That's not evil. Okay, shout out to Kubo for reminding me to record this. We're going to start with this integral, which I want you guys to have a sense of a sketch of what this graph looks like, meaning you know what 1 over x looks like. So 1 over x cubed should not be substantially different. And for the purposes of view, the graph is not different. The only thing that really changes is that it becomes more of a 90-degree turn because it's just a sharper change as you hit that. You still have the ordered pair 0, 0, and -1, -1 as the graphs. You just have a sharper changeover in it, which means that, remember, for values greater than 1 in the denominator, you're going to see some convergence of that. And that's not only going to happen in this region, this region here, where I'm greater than 1, but that sharp turn also happens in that region here, which enables you to have some area to work with. So the integral from 0 to 2 should look something like this on a graph, where we're going to shade that area now and do it. And so it's not a limit to an infinity as we go right, but it actually is about the same kind of limit to infinity as we go. You just need to see, is it truly, are we going to have that, and is it going to approach the x-axis, the y-axis fast enough or not? So we separate this into a limit, and I get the limit as a approaches 0. This is a one-sided limit, so we're approaching it from the right. It has to be a one-sided limit. Integral from 0 to a of dx over x cubed. Oh, it should be a to 2, sorry. Okay, so now integrate it. Still have the limit as a approaches 0 from the right of, this is going to become -1 over 2x squared, evaluated from a to 2. If I take out the -1/2 as a constant multiplier, and I can throw that out way in front of the limit if I want to, then all I have is 1 over 4 minus 1 over 8 squared. Then we evaluate the limit. The 1/4 is incidental. It's not going to change anything. But what's 1 over 0? Infinity. So I end up getting a 1/4 minus an infinity, which unfortunately means that despite how close we thought it was coming, it's not coming fast enough. This is 1/4 times an infinity, which is an infinity, or better yet, actually it's positive 1/2 times infinity. It was a negative infinity to begin with. But the more important is that we can say that this diverges. It's not really important to talk about positive, negative area. It's important to say that the sum doesn't exist. There is no sum. And so that diverges means that we don't truly have a sum in place. We can't find or evaluate an integral on that. Next, I want to show you how this works for something like this, where you're going to be tempted to make a mistake that I don't want you guys to do. We're going to do a similar problem. This is a problem where now 0 occurs in the middle of the interval. So I get -1 to 2, and I know that 0 is contained in there, which means that the discontinuity is occurring in the middle. The question here is, if I graph this again, and I get something that's symmetrical about the origin, and we want to graph from -1 to 2, can I cancel the areas, the infinite areas of the negative and the positive, and evaluate the integral? Let's go. I got the limit as b approaches 0 from the left of -1 to b. So I'm splitting this around 0 of 1 over x cubed dx plus the limit as a approaches 0 from the right of the integral from a to 2 of 1 over x cubed dx. So what I've done is I've split this around 0. I've created 0 from the left on the one coming in from the left and 0 from the right on the one coming in from the right. Now, for reasons that we've already established, that I don't need to go into again because we've actually already evaluated these integrals, this would end up being negative infinity, this would end up being infinity. So I have negative infinity, which is a divergent sum, and I have positive infinity, which is a divergent sum. Even if it's negative infinity plus infinity, the sum of the two of those we have to say diverges. By rules of this, we cannot add infinities to each other. So the rule that you guys are going to have on these is if any part of a sum diverges, any part of a sum diverges, whether positive or negative, the whole thing does. You're going to get these sums when you split your integrals up into multiple pieces. But even if even a single one of them diverges, then the whole thing does, which can speed things up because you only need to establish that one part is divergent to say that the whole thing is.
What do you mean by divergent?
Diverges is the opposite of converges. So think of convergent as an infinite sum of numbers that never gets more than a certain limit, and that limit is what it converges to. So even in this sense of an integral, if this were to have a sum, it wouldn't actually truly be a sum so much as a hardcore, like closest possible limit that this is approaching. That's what converges means. Diverges is what yesterday we referred to 1 over x does as far as a sum, that even though the value goes to 0, the infinite sum goes to as many big numbers as you want. So the difference between convergent and divergent can be so microscopic in terms of how much that curve goes. But what it's saying when we say that 1 over x as an integral is divergent is we're saying that even though this value gets infinitely close to 0, the sum's not going to get infinitely close enough for it to add up to a particular value. It will just forever go to infinity. Yes, Paulina?
So for the first one, why couldn't you just say infinity?
For the first one?
Yeah.
You can, but diverges itself is going to answer the question of what is the integral. This terminology of convergent divergence is going to we're going to use much more when we talk about sequences next chapter. So I'm just trying to introduce this a little bit now. Okay, next example. The integral from 0 to infinity of dx over, oh, sorry, it's number 4 on mine, but I did number 1 yesterday on this. Okay, that should be number 2 then.
How should that be number 2?
Because then this is number 1.
Oh,
yeah. Okay. This is a case of where, look at your denominators, look at where your discontinuities are. There are 2 of them. Our integral limits are not within the -1, so we're fine there, but we're not fine at the 0. And given that we're starting with a divide by 0 and we're ending with an integral to infinity, we need to create 2 integrals for this. Basically, take this and split it into the integral from 0 to, pick a number. Yeah, I'm going to go 1, 2. Plus the integral from 1 to infinity of dx over root x times x plus 1. So you get to pick the one, whatever number you want. There will be times where that number might conveniently be an e or something that makes numbers happen a little bit nicer, but here it clearly should just be a 1. And then we're going to create 2 separate limits. Limit as, okay, so we need one for this 0. So a approaches 0 from the right of the integral from a to 1 dx over root x, x plus 1, plus the limit as b approaches infinity of the integral from 1 to b dx over root x, x plus 1. Okay, then you actually do have to try to figure out how do you evaluate this integral. Any thoughts? I'll kind of start. Try u is equal to root x, which means that u squared is equal to x. When u is equal to root x, du is equal to 1 over, or 1/2 x to the negative 1/2, which is 1 over 2 root x dx, which means that dx is equal to 2 root x du. Do you guys remember those integrals where you're doing the u substitution just to rewrite everything? Not necessarily because it's going to cancel anything out, but just because it's going to work everything differently. That's where in an integral like this, it's useful to try that. So let's kind of start with what the substitutions are doing. If u squared is equal to x, then, well, this denominator becomes, we said u is equal to root x. That just becomes a u. Then we have x plus 1 becomes a u squared plus 1. Then we have a dx, which is 2 root x du. That hasn't changed everything over into the u's yet, except it kind of has. Yes, Pakina?
Does the limit have to change too?
The limit itself, your limits of integration, they do. That's a nice call. U is equal to root x, so this becomes root a to 1. Isn't root x the same thing as u, though? So then those can cancel. And we can pull the 2 out. So knowing all that, and without too much effort, I can actually factor a 2 out of the entire thing and say 2 times big limit as a approaches 0 from the right of the integral of root a to 1 du over u squared plus 1 plus the limit as b approaches infinity of 1 to b, 1 to root b of du over u squared plus 1. Do you see where the root b's and the root a's came from? Remember, you have to plug your limits of integration into the u equals root x. So then let's evaluate these. 2 times. So this integral is an arctangent. And I'm going to do the limit a approaches 0 from the right of the arctangent of 1 minus the arctangent of root a plus the limit as b approaches infinity of the arctangent of root b minus the arctangent of 1. Okay, now we evaluate. What's the arctangent of 1? What's the angle whose tangent is 1? Yeah, that's pi over 4. Minus arctangent is 0. Plus arctangent of infinity, pi over 2, minus arctangent of 1. And everything just kind of collapses down and becomes pi. Stop recording.